Hello everyone. Is my audio clear?
Yes, sir.
Okay, we'll start in 2 minutes. Okay, and today we'll discuss the week 10 activity questions, and also uh, today we'll discuss a little bit more about the small signal things. Okay, I told you in the last class that I will tell you in details about in small signals. So today I will discuss the small signals of MOSFETs, and if time permits, I will discuss some concepts also. Oh, that concepts will help you a lot for solving more questions and also encourage you to know more about MOSFETs. Okay, so that's why I today's class is a little bit lengthier, maybe lengthier. I don't know if I can cover it in fast manner. If I'll cover, but the thing is, you have to understand each and every concepts. This concept today I'm going to discuss. It's very important. Okay, if some of your friends are not attending the class and willing, like they know about the class and not attending the class, then tell all that today's class will be very helpful for them for solving problems, as well as today's class. In today's class, you will learn something which you didn't learn in the classes, regular classes. Okay, we'll learn something out of the box. So tell them if they want to join, they can join. Okay, guys, we'll start now. Okay, so is my screen visible to everyone?
Yes, sir.
Okay, just give me one second. This is like that. What are the other questions? Okay, so is everything clear? Can clearly see the questions also?
Yes, sir.
Okay, so we'll start now. So, is there any problem in the first some theory questions? Okay, I will quickly cover this question. Then, after covering the questions itself, I can go to the concepts. So please tell me, is there any doubt in these questions? Okay, I just quickly cover the doubt and then only I will move to the concepts. Okay, so first my duty is to cover these doubts. So tell me, is there any doubt in the question? And like I will quickly go through those doubts. Did you solve the questions? All questions are solved. Did you go through it?
Sir, question number 11.
Okay, before question number 11, is there any doubt? I'm asking to everyone. If there is any doubt, then tell me, I will discuss. Okay. Okay, so I'm moving towards question number 11. Okay. Okay. So can you tell me what is the circuit is?
So this is this circuit on the concept of current mirror.
Yeah, this is a current. This is a current mirror circuit. Okay. So whatever be the current here, whatever be
Should be
the,
the same on the all transistor.
it should not be the same. Okay, it depends upon the W by L ratio that is given. Okay, if nothing is mentioned, then you have to take the all transistor are in same sizes. Okay, are of same sizes. But the thing is, it the concept says that it depends upon the how much current you are pushing to the reference, like to the uh, reference mass that you are taking, and that current should be the replica, that should be like uh, mirror through the other MOSFETs for multiple times, but it may be same, but it doesn't mean that it should be the same. Okay, so whatever be the current here, or this current will be mirrored here. Now here I have given in this given series the MOS are identical. Now here all MOSs are identical means whatever be the current is IREF is, this whole IREF will be copied to here, and here. These all four MOS will carry the same current. So if all four MOS carry the same current, then this will also IREF. This is also IREF. This is also IREF, and this is also IREF. Can you see my pointers?
Yes, sir.
Okay. So if all are IREF, okay, then four IREF will come through this from this drain. Okay. So if four IREF came, so whatever we draw here, four IREF into RD. Did you got or not?
Yes, sir.
Okay. Just give me 1 minute. How can I do it full screen? Just give me 1 minute, okay? Like if I don't full screen it, then it will be a problem for me. Uh, yeah, this is option, but why? Yeah. Okay. Now see. So if I asked about whatever be the V naught, what is V naught and what is I naught. Now I naught, I just now I told that I naught. I naught is, what is the I naught? I naught is ID. Okay. So I naught will be, so whatever be the current is flowing through the our RD, that is V naught, and V naught by RD will be our I naught. Okay. So just now I told so for this configuration ID will be I naught. Is there any doubt?
No, sir.
So I naught is 4 IREF, and IREF is 4 into IREF is 5 milliampere is given. Now 20 milliampere is our I naught. Now V naught will be I naught into RD according to the polarity given. According to the polarity given, V naught will be I naught into RD. It will be positive. Okay. So I naught is 20 milliampere and RD is how much? 5 kilo.
5.
So 100 volt. Okay. Now let's suppose I am modifying this question to a little bit. Okay, let's suppose that these three, whatever be the transistor, okay, these three have some, this is some W by L. Okay, do you know what is if I write W by L here, do you know what does it mean? First of all, tell me. If you don't know, then I will explain what is W by L. Then I will move forward to other questions. If I mention something that yeah, this is W by L, so what does it mean? Do you know? If you don't know, please feel free to tell. I'm asking to everyone. Guys, please reply. If you be quiet now, this session will like this session will take so long. And if this session is so long, I'm bounded by some times. Okay, if if you guys don't reply to me, then the thing is you will lose some concepts. Okay, please be active. If I ask something, please move forward for answer.
It is a ratio of width by length.
Yeah, width by length. Then what does it signifies actually? I'm asking about that. If someone knows, then tell me.
Sir, please explain it.
It is
Please explain,
okay.
W.
Please explain. Okay. Then see.
I
Please tell
think
me.
current is depend upon W by L ratio.
Yeah, exactly. Current depends upon how it like I am saying that how it depends. Okay. Now please tell me what is the current through a MOSFET. Let's say this is ID in saturation region or whatever be the region is. Okay. Let's say you are I am asking for saturation. What is the current expression? Hello. Okay. This is 1 by 2 mu n Cox W by L VGS minus VT
VT.
whole
Okay.
square. If this is triode region, if the MOSFET operates in triode region, okay, many can say what triode region is equivalent to linear region. Okay, if this is linear region, then this will be 1 by 2 mu n Cox W by L to VGS minus VT minus VDS. Sorry. It will be VGS minus into VDS minus VDS square. Okay, these two equations you know or not? First of all, I just take those equations from your class.
Yes.
So VDS square divided by 2.
That's why I taken 1 by 2 here.
Oh.
Please notice I multiplied here 1 by 2. I multiplied here 2, and I take this 1 by 2 multiple factor here, and that's why I didn't divide it by 2 here.
Okay, sir.
You just learned this form. You learned this form actually. You just learned this form. I just take this 1 by 2 factor outside. Okay.
Yes, sir, got it.
Now see why I take this factor outside, because see in both those equation, this 1 by 2 mu n C of W by L factor is common. Now the thing is, this is a constant actually. When some manufacturer gives a like sells a MOSFET, na, he actually mentioned this constant because see mobility of electron is constant. Oxide, like capacitance of oxide is constant. This W by L ratio is made according to the specification which is mentioned by the like buyer. Okay, so this whole term is constant. Okay, that's why this is mentioned with the name of K. Okay, if it is a NMOS, then this is represented by Kn or sometimes Kn prime. Okay, and if this is a PMOS, that is represented by Kp or Kp prime, whatever be the notation. It is like these notations are used according to the manufacturers. Okay, so Kp or Kn or Kn prime or Kp prime, whatever. Don't think much about that. This is a simple constant. Okay, and this is actually specified because this is constant. Whatever be the changes, what is in our hand? This VGS minus VT. Okay, and VDS also. If I apply some drain voltage, drain to source voltage, that is in my hand. If I apply some gate to source voltage, that is in my hand. Okay, that will not specified by the manufacturer. Okay, Now this VGS minus VT is called as overdrive, gate overdrive voltage. Okay, gate overdrive voltage. Okay. Okay. Now this is just an information. You don't need to remember this, but if you remember this will be fine. Okay. Now you all guys are going to be engineer. This kind of technical terms, if you know, then it's very good. Okay. It doesn't mean that you have to buy hard it. Just I am writing because this is a simple information facts. Okay. Now see both of these equations. The thing I want to point out this both of the equations depends on this W by L ratio. Now for a technology, okay, this L is fixed because L is taken as L min. This L is fixed. Okay. So let's say now the technology node is became 2 nanometer, 3 nanometer. Okay, this kind of things. It doesn't mean that this L min is 2 nanometer, 3 nanometer. It depends upon what process, by what process the MOSFET is made. Okay, let's say this L is this. Let's say this L is 0.42 micrometer. Can you imagine 0.42 micrometer is 420 nanometer? 420 nanometer. It's nanometer. Means 420 into 10 to the power of minus 9. Now see how small is this? Is comparable to one atom. Okay, it's like order of magnitude is higher than an atom actually. Okay, so this is how our technology goes. That small is our MOSFET. I'm talking about practical thing. Okay, this 0.42 micrometer is a it's mentioned in the PDK of the sky water. Okay, so just imagine the thing. It's 420 nanometer is the minimum length. So what is the called as minimum length? That minimum length define that a chip fabrication machine, okay, can fabricate the minimum dimension is 420 nanometer. It can like fabricate a MOSFET minimum length that is lesser than your hair also, width of your hair. Now just imagine the thing. Okay, that's cutting edge technology is used in VLSI industry. Now that is the fact thing. Just I just discussed that how fascinating the things are in the real life. Okay. Now see this L are kept as constant. Okay, as a designer, we vary only this W. This W. Okay, what is the W? W is the width, and what is the L? L is the length. Now width means what width? At which parameter we are talking about? We are talking about the gate width. Okay, MOSFET width. Okay, this is the width of the MOSFET, and this length is the length of the gate. Okay, now if I draw something, if I just tell something you can't understand. Let's say I draw a MOSFET. Okay, this is the bulk. These are the two diffusions. This is the P bulk. This is N plus diffusion. I am drawing a NMOS. Okay. Now this is the gate. This is our metal. That shaded region I am setting up. Okay. This is oxide. This is oxide. Okay. And this is our semiconductor bulk. Okay. This is metal. That's why it is a MOS, metal oxide semiconductor. Okay. And do you know what is the full form of FET? MOS is metal oxide semiconductor. Do you know what is the full form of FET?
Field effective transistor.
Yeah, field effect transistors. Okay. So I am talking out now. What is the dimensions? This is the L I mentioned now. This is L I mentioned. Whatever be the length of the gate, and what is the width? Now this for 3D, this will be like this only. Okay. Okay. See, this is our train. Okay. Now if I draw the top view, you will understand more. I'm drawing the top view. Okay. So this is the side view. Sorry, front view I just drawn. Now this is the our gate. I'm talking about these dimensions. Okay. See, this is L. I mentioned this is L. This is the width. As a designer, we have some control on these parameters. Just as a designer, we have only the control on geometry of that particular device, nothing else. Okay, or some parameters. Okay, that you don't need to remember now. Okay, for a undergrad level, this is way more enough information. Okay, so you understand, all guys. I'm asking, all guys understand these concepts. Okay, I'm just giving you a physical interpretation what we are going to learn. I'm talking. Hello, I'm asking everyone. Did you understand? Are you
Yes,
following
sir.
what? Okay.
Yes, sir.
So everyone is following the whatever I am doing, or I am going so fast. Is it okay for you? The pace?
Yes, sir. Okay.
Okay. Now see, this is W. Okay. So the thing is, this W is in our hand. So if I make some bigger W, the current will be higher because this I D is direct. We can say the directly proportional to W. Now if I make higher W, the current will be higher. Or if I make higher L, the current will be lower. Or if I lower the L, the current will be higher. Now someone says that, sir, why to increase only W? You can also decrease that L also. You can also decrease L. That will also make our current higher. Okay. But just now I told this minimum length is defined for a technology node. Okay. You can't make lesser than that. Like there is a fabrication limit. Below that limit, you can't make like you can't lower this length of the gate. Okay, that is the thing. We can't do anything about the length. That is why we are always trying to manipulate the W according to our need. Okay, you understand the reasons? And all these things are constant. We can't do about that. We can't do anything about that. Okay, so we, as W and L, we have something. And also someone can say that, sir, we can also manipulate something on this VGS minus VT. Okay, VDS, this thing is also in our hand. The thing is, we have like in our hand, because that this is the supplies. Whatever be the supply we give, that will be provided to the MOSFET, and this is in our hand. Then the thing is, you can't do more. Like, let's say for a MOS, in a MOS circuit, you are like you have a limited supply of 5 volts. You can't do above that now. These voltages are also applied. Now someone can say that why that limitation. So if those limitations are not there, you will be end up with a end up with a 1-ton battery for a laptop itself. You can't afford that, right? We can't afford that a big bulky battery for a small laptop. You can't afford a big bulky battery for a small phone. Then while carrying your phone, you have to carry another bag which are having a 10 kilo battery. Okay, so you have a limited voltage supply also. Okay, voltage and voltage supply also. The thing is, that is also limited. So the thing is, we just have this W and L in our hand, and this VT. Do you know what is this VT? What is this VT?
Threshold voltage.
Yeah, threshold voltage. For a particular MOSFET, this threshold voltage is also fixed. Yeah, it can vary. This threshold voltage can vary with VDS. Okay, I'm not going about that. That called is body effect. That is so complex. Okay, like, not so complex. Okay, that is a different thing. We'll distract to our main topic. That is threshold volt. That is also, you can take that. This is for a particular MOSFET, that is fixed. So, okay, so we can lower the threshold voltage to increase the ID also. Okay, so only thing in our hand is W by L. Now see, if I make for this question, if I make this is W by W, this is 2W I make. Okay, then tell me, and all the things, this is a W, this is W, this is W, this is W. Okay, now tell me what is the current here now?
ID.
ID in terms of IREF. Current here is obviously ID. Okay, here is ID, it is written. I'm saying about in terms of IREF. What is ID now? I just did one change. These all are W that was previous. These things are in previous. Okay. This previously this circuit is this much. Now I change this only W to 2W. Okay. Now
But
just
with 2 ID,
okay. So this is, let's say this is IX current is flowing here. So this is 2IX. This is 2IX and these all are IX. These all are IX, IX, IX. Okay. Now what? So 5IX equal to ID. Okay. Now IX we can directly say that IX equal to IREF, sir. So ID equal to how much in terms of IREF? Hello?
5 IREF.
5 IREF. Everyone got the answer or not? Everyone got the answer? 5 IREF. Okay, I'm thinking, I'm guessing that no one gets. Okay. Okay. See, this is IREF. This W by L and this W by L is same. So this is also IREF. Hello, I'm audible, guys.
Yes, sir.
Yes, sir.
It's extremely sorry. That thing is, these hostel internets are so poor. Just give me some time. Okay. Just you can see my screen, na?
Yes, sir.
Yes, sir.
So what I was discussing, the last thing, whatever you like, what is the last thing? Hello. Actually, I kept talking and I didn't even realize that I got out from the meeting. Just tell me what is the last thing I was. Hello. I didn't.
So what is ID? We have to find ID.
Okay. So yeah. Now see. So these three are IREF, right? Okay. Now I am asking about what is the current of this branch, like the last branch, the transistor which are having 2W. Hmm? Can anyone answer? What is the what is the current to the last MOSFET? If you guys don't know, you can say we don't know. Explain. The thing is, you don't have to be quiet. Just I'm saying that if you don't know, then you can simply say, "Sir, please tell me." Okay. So the current through the just now I told the current is directly proportional to the current is directly proportional to the W. Now, if this is W, this is 2W. Whatever is the current here, the
290.
two times of the IF. Okay. So this will be 2 IF because this is the current mirror. A simple current mirror. If I draw a simple current mirror, okay, like this, and if I say this is, let's say, 5 milliampere, and this is W, this is 4W, then this will be 5 into 4. Just think, just simple as that. 5 into 4, this will be 20. Now, if this is IREF, this will be 2 IREF in simple way. Okay.
Yes, sir.
Okay. So total current flow from here will be 5 times IREF. Okay. Now, according to that, that voltage will change. The operating points will change. A simple thing. Okay. Now, one thing you guys have to. Okay. Now I will discuss that thing later. Just say that. Is there any another doubt in this PDF? I'll quickly discuss those. Then I'll go move forward for the next. Is there another doubt? Do you know what is this circuit? This circuit. There is a special name of this circuit.
CMOS, sir.
CMOS.
CMOS inverter circuit.
CMOS inverter circuit. Yes. Is there a doubt? Guys, fast. No doubt. Anyone want to discuss any questions? Okay, I will discuss. If not, I will move forward for the concepts. Hello? No doubt in activity questions. Anyone else? Swastika has no doubt. Other guys? Okay. Okay, then I'm moving forwards toward the concepts. Okay. 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 Now see, first of all, tell me that we have some components R, L, and C. R, L, and C. These components we previously have. Then why we move forwards this BJT, MOS, okay, these other things. Let's say op amp. Why like why would I interested in this particular components? Okay, we have those already. Those components were there. Then what is the need of the other components in the circuit?
For switching and amplifying purpose.
Okay, for switching and amplifying circuit. For switching, we have a diode itself. Okay, so switching is not only the only region. The thing is main is the amplifying region. Amplifying. Okay,
Okay, sir.
so amplify. You have to amplify some things. Okay, but why we need amplifying some things? That's the correct answer. Some amplifier, as an amplifier, these particular components should be needed. And so you are saying that we can't make an amplifier with these. Then why is it so? Why this amplifier cannot be made by this? Then why is it so? And why you can make amplifier with these circuits? These particular concepts should be in the mind while studying this. First of all, this R, L, and C. Achha, first, tell me, do anyone knows this? Why is it happening? Hello? Am I audio video clear?
Yes, and now is audible, but screen is not visible.
No, screen is not visible.
Yes, sir, visible now.
Okay. I asked that why this amplifier, why for amplifying circuits, why this is needed. Guys, can you hear me? I don't know that I am clear to you or not. My voice is clear now. Hello?
Yes, sir.
Okay. Okay, I'm assuming that you guys don't know. Okay. The thing is, these R, L, and C, these are called as passive components. With these passive components, we can't make an amplifying circuits. Okay. For amplifying circuit, then the question came that why? Why is it so? With the passive circuit, why we can't make amplifying circuits? Because this passive circuit can give the maximum gain of 1, not more than that. A passive circuit cannot provide a gain of more than 1 in a particular circuitry. Okay, that's why this passive circuit cannot act as an amplifying circuit. Secondly, for an amplifying circuit, we need these active components. Okay, now that's why we need this particular thing. Okay, now this MOS, BJT, op amp, this have some different kind of, these are one common thing is there. They are dependent sources. First of all, they are dependent sources. They are so. This is clear that for making an amplifying circuit for active circuit, we need some dependent sources. Okay, so how many dependent sources still now we know? How many dependent sources are there? First of all, answer me. Do you know about any dependent sources? If not, I will tell. Okay, if no, then answer. Hello? Hello? 4 dependent sources there. Swastika, you can tell them, you can on the mic also. Okay. If you're not comfortable, then it's okay. The thing is, it's not possible to change the tab multiple times and see what your answer, you guys answer. Okay, so 4 dependent sources are there. So the 4 dependent sources are current control, current source, current controlled voltage source, voltage controlled current source, and voltage controlled voltage source.
source.
Yeah. Now, can you tell me any current example of current control current source? Okay, we know that these are the 4 controlled sources. Okay, now these are the theoretical name. For making a circuit, we have to like go and tell, give me this component to a saw. Now, what is the component name here? What is current control current source? Do you know anything? It is already written on the page. Now see, we have till now I have wrote 6 components in the page. Okay, first thing R, L, C, BJT, MOSFET, op amp. These are only 6 components I have written here. So from this, one of or multiple will be current control current source. Okay, so the idea of current control current source, we are pushing some current. We are pushing some current to a black box. Okay, and you are also getting some current. So this current is controlling this current. Let's say this is I. Okay, this is I. This is, see, this I out will be a function of I. Just simple thing. That's why this is called as current controlled current source. Now, till now we have already studied a thing like that only. Okay, we are pushing some current into the base of something, and we are also getting something. What is this? We are also getting some current. What is this component? Hello?
Yes, sir.
This is BJT, not yes, sir. Okay. So this is current control current source is BJT. Do you know what is current control voltage source? Is there anything you till now? I think till now you don't know anything about current control voltage source. Do you know anything? Have you studied about any component?
This op amp. Right.
No. Op amp is not current control voltage source. Okay. Anyone else? But op amp will come. Op amp will comes in some of the sources. Okay. Some of the op amp is one of the control sources also. So this is still now I think you didn't study about it. This is a trans impedance amplifier. Okay, a trans impedance amplifier is a current controlled voltage source. Okay, so now it's still about voltage controlled current source. This is also mentioned
MOSFET.
a MOSFET, because for a MOSFET we provide some voltage to a gate of the MOSFET. Okay, and we get some current as a drain current from this MOSFET. So we are applying some voltage Vi, and we are getting a current ID that is like a function of this Vi.
Yes, sir.
Okay, that's why is the current control voltage, voltage control current source is a MOS. Now, what about current control voltage control current source? So for idea of voltage control voltage source, we have to push some voltage, we have to give some voltage. Now this is a black box, and we'll get some voltage also. Okay, or you can say that we can give some voltage with respect to ground. Okay, this is, let's say this is ground. Okay, some Vi, and we will also get some voltage that is with respect to ground. V out. This V out should be a function of Vi. Okay, so that is a op amp. Till now, did you guys studied about op amps? Do you have an idea on op amps or not?
No, sir.
Okay, so today we will not discuss anything about the op amp. Okay, so this is the voltage control voltage source. Now see, today I will discuss the small signal about the MOSFET. Okay, now please be attentive in first, like for the next half an hour. Be attentive and be like ready for the answers. If you don't know, please tell me that we don't know. Okay, and if you do know, then reply fast. Okay. See, we have a MOS first. We have a MOS circuit. Okay, this is our drain, this is our source, this is our gate. Okay, now to use this MOS, okay, first we have to bias it. Okay, so a biasing mechanism should be there in the circuit first. So there are some biasing mechanisms. Okay, biasing means biasing. First of all, tell me what is the meaning of biasing?
To set the operating point.
To set the operating point to what? Yeah, it's correct answer, to set the operating point.
To flow the current.
Yeah, to flow the current. Like what is the nature of the current then there? I'm asking about, it's a linear or triode or cutoff something. Okay, what is the region of operation?
It should be the saturation region.
Okay, it should be the saturation region. So first of all, this biasing mechanism is needed because of to set the MOS in saturation region. Now the immediate question came that, so we told that, sir, biasing mechanism is needed to use this. Okay, then the question came, why biasing mechanism came. Then we got the answer, biasing mechanism is needed to set the MOSFET in saturation region. Then immediately question came that why we need to bias this MOSFET in saturation region. Why?
To on the MOSFET.
Okay, to on the MOSFET, we can bias the particular MOSFET in triode also. Okay, there are three regions: cutoff, triode, and saturation. This is cutoff, no ID. ID flows here. ID also flows here. Then why only this, not this? Why not this? Now this is this is a question that is asked in many interviews also, and also this particular question is not clear to many of you guys. Okay, and yeah,
At triode region, the current will start increasing.
Okay, then what is the problem then? Let's say
But
let's say
the main point is, MOSFET should be the on.
MOSFET should be on. Okay, then if current is increasing or decreasing, then obviously you are saying that this switch is on. If current is flowing, that itself means this switch is on. See, if you are saying that the current will increase or decrease, that answer is not that much correct. You are applying some VG, your VGS. This is your ID. Okay, this is your input voltage. This is your output current. Okay, and the graph is, we know, like this only. Now let's say if you set a particular voltage here, bias means if you set a voltage, if you set a particular fixed voltage. Okay, now if you say this V1 is VI is given. Okay, now according to this VI, some ID we will get. Some ID, let's say 5 milliampere we get. Now the increment or decrementing particular increment, like, so increase or decrease things will not is that much valid here. If this VI voltage varies, if there is something, some small VI varies here, then this I can vary. This I can vary. That's fine. But we are not saying about this only. We are saying about the operating point. So for a particular voltage, you will get a particular current. And in this region also, the MOSFET is on. MOS is on. Okay. Now, why only this? Why only this particular? What to say? Saturation. The answer is, why did we? The answer is, we have to go. We have to step back a little bit. Why did we start using MOSFET? You guys answered those questions. Why we need a MOSFET? You guys already answered. Why we need a MOSFET?
For amplification.
For amplification, correct. So for amplification, we need to bias the MOSFET in saturation. Then again the question came, why? For amplification, we have to, we'll give some small thing, and we want some big thing. This is the main purpose of amplification, right? To do this properly, okay, this amplifying is done by a factor, okay, that is called as GM, that is transconductance in a particular MOSFET. We'll come about that. Don't worry. I will tell you what GM is. Okay, but thing is, that is a tool. Okay, and also there is one tool, that is MOSFET resistance, MOSFET drain to source resistance, that is R0 or RDS or RDS. Okay, so this R0 or RDS are needed for the amplification thing. Now the thing is, the greater this GM and this R0, the greater the amplification. Okay, and the greater range we will get from the amplification range. So we need to maximize this GM and this R0. The thing is, we'll get maximum 2 of this in only saturation region only, not in other region. Okay, that's why we need the MOSFET to be in saturation. So what is the answer of this why?
Sir, please explain it again.
Yeah, I will explain. Don't worry. I will explain it. I will explain it while discussing GM and R0. Okay. So the answer of this why is, in this saturation region, this GM and this R0s are very high. And what is this GMs and this R0? This GM and the R0s are the tools of amplification. That is the property of a particular MOSFET that amplifies the signal. Okay, till now this part is clear. I will tell about GM and R0.
Yes,
my main point is this why answer is clear now.
Yes, sir.
Okay, now I tell a lot of things about GM, R0 and these things. Okay, now the thing is, we have to discuss what is GM and what is R0 and these things. Okay, and one other thing, this GM and this R0, these are small signal things. Small signal. These don't come in the picture while the MOSFET are biased in DC. Okay, to bias this MOSFET, we have to have a DC mechanism. Okay, let's say this is our supply voltage. Let's say this is VDD. Typically, what is VDD? VDD is the highest supply voltage that we have. Okay, we have in a particular circuit, we have a fixed voltage supply. Let's say this is in a particular circuit, this is 5 volt. Okay, like that only. Okay, the 5 volt, and the lowest is VDD. Ground. Okay, it's not necessary to be ground. We can have the minus VDD also, but don't go to that complications. Okay, let's say we have some 0 volt. Now we have that MOSFET. Now the MOSFET has to be biased, and this MOSFET will drive some load also. Let's say this is the load. Maybe the load may be any of the terminal in drain and the source. It need not to be in the drain only. And let's now take this is the like our load, and also this resistance can be used for only biasing also. It need not to be the like we need to use the load is in this particular branch itself. Okay, I'm just showing for example. So for biasing a MOSFET, this is our MOSFET. For biasing a MOSFET, we need to create a saturation region in this MOSFET, right? For what is the condition for saturation region? Tell me first.
VGS should greater than VT.
Okay, that is not the correct answer. Okay. Anyone knows the correct answer?
Sir, VDS greater than VGS minus VT.
VDS. Okay, that is the correct answer. Okay. So this is our VGS. Okay. This is the gate source voltage. This is the drain source voltage, VDS. Okay. And okay, this, let's say this is 5 volt. Okay, let's say this is 3 volt. Okay, now VGS is, what is VGS? 3 volt, because this is ground. 3 volt. VDS, what is VDS? Is 5 volt. Okay, now let's say for this particular MOSFET, the manufacturer told me this MOSFET has a threshold voltage of 0.7 volt. Okay, VT equal to 0.7 volt. So our condition of biasing a MOSFET is VDS, drain to source voltage, has to be greater than equal to what? VGS minus VT. Now here VDS equal to 5 volt and VGS minus VT is 3 minus 0.7. Now this is 2.3. Is this greater? Yeah, it is greater. So this MOSFET, we can say that this MOSFET is in saturation region. Now we can use this MOSFET as an amplifier. Okay. So far is this clear?
Yes, sir.
Okay. So just like in the previous particular slide, now I discussed also the current equations. What is it? Yeah, there it is. So this is the saturation region. This is the condition here is VDS should be greater than equal to VGS minus VT. And the condition of this, what is this condition? Can you tell me? Obviously, inverse of that, VGS minus VT is greater than VDS. Okay. And for both this condition, there is a common condition. That is VGS has to be greater than equal to VT. Okay. The thing is, if the MOSFET did not turns on, then we can't say about the current will not flow. Then there is no question of this saturation, triode. These things only came into the picture when that MOSFET turns on. Okay, if I draw the graph of the MOSFET, okay, this is ID. Let's say this is ID, and this graph you know from your class itself. This is VDS, drain to source voltage. Okay, this graph varies like this. Okay, for practical scenario, this graph is not constant with the voltage. Okay, this has a particular slope. This is slightly exaggerated. This is a particular slope. Okay, so you don't need to remember this. Okay, these things you don't need to remember. Okay, that includes actually body effects. Okay, that thing is not needed. So the thing is, till this, Do you know what is the point? This point. This is VGS minus VT. Okay. This thing, this region is called as linear or triode, and this region is called as saturation. Now you can say that saturation with increase of drain voltage, that drain current does not varies. Okay. So if, can you tell me one thing? If in a particular system with the increasing voltage, let's say this is V and this is I, okay, with the increasing in voltage, if current does not varies, okay, what does it mean? What does it mean? Am I connected or not? Okay, I'm connected. Hello.
It will be constant.
Yeah, it's constant. That what does it mean then? If with the increasing voltage, if current does not change, what does it mean? Okay, I'm asking a simple question then. Okay, that is let's say our voltage is this axis and our current is this. Okay, so I am increasing the voltage, but the current is still zero. Current is not increasing. What does it mean? Say we have a black box. We have a voltage supply. Okay, we have a voltage supply. Okay, this circuit is completed. Okay, and we find that this current is zero. What does it mean?
I think the resistance will be high.
High means what? How much high? Okay, you answered the question. It's correct answer only, but a little bit modification should be needed. So let's say this. So if current is not flowing, that means it is going to resist the current very heavily, right? It is not allowing the current to pass. So what is the resistance then? Resistance will be V by I. Now V is something value, okay, and I is zero. Now this is what is the something by zero? Something by zero is infinity, right? Now this signifies that this particular circuit, like giving a very high impedance in this particular organization. Okay, now for this circuit some current is flowing. Okay, but the thing is, with the increasing voltage, this current is not current is not increasing. Let's say at 1 lakh volt, for this circuit I was talking about, that let's say at 1 lakh volt the current is only 1 ampere. Okay, now this is the resistance then. Now let's say in the particular same circuit, another guy gave 1 crore volt and the current is still 1 ampere. Okay, then resistance will be once here. Okay, let's say some guys applied 100 crore volt, then the resistance will be 100 crore. Okay, so there is no upper limit. Whatever voltage you are applying, that is not allowing the current to flow. That means the resistance is very high. That's why I'm saying that at saturation region with the increase in voltage, the current is not increasing, right? If with the increasing voltage, if the current is not increasing, that means the resistance that will provided by the MOSFET in saturation region will be very high. That's why I told that for amplification, GM and R0 should be very high. That's why the R0 is very high in the saturation region, not in linear region. In linear region, the current to voltage graph is like this. So if you are applying some voltage, you are getting some current, and there is a linear operation. This particular R on will be finite. If R on is finite, then that will limit our amplification also. That's why in triode region, this R naught is much smaller than saturation region. That's why you use a MOS in saturation region for amplification. Now, only thing to discuss is this GM, right? Now, see. Hello, am I audible?
Yes, sir.
Now, this much I discussed is clear. Whoever is asked, someone is asked why this R naught and GM concepts are not clear. Now, the R naught concept is clear or not?
Yes, sir.
Okay. Okay. Now, this is the organization we have. Now, for biasing circuit, we use this only. Okay. So, wheels R1, R2. Okay. So, this is VDD. Now, this is a simple voltage divider because no current will pass through here, because the MOSFET, we know that the gate current is 0. Okay. We know na the MOSFET gate current is 0 or not. This we guys all know na,
Yes, sir.
Yes, sir.
because there is an oxide layer, that is a insulator layer. That oxide layer will not pass any, like, that will not allow to pass any charges to the from the gate to body. So this is why we use this particular a particular example. This is let's say 2.5 kilo, 2.5 kilo. This is also 2.5 kilo. Okay, let's say this is 5 volt. Okay, uh, and let's say this is 3 volt. Okay, now what the voltage, what is the voltage here? Can you say me what is the voltage here? This VG, gate voltage. Can anyone answer this simple voltage divider?
R2 by R1 plus R2 into VDD.
Yeah, that is given. R1 and R2 is given. What is the answer? I'm just telling you. This is 5 volt. This is 2.5K. This is 2.5K. You want to know the answer here. Like, I want to know the voltage here. What is V here? How much?
2.5.
2.5. Correct. So this will be 2.5 volt. What is the drain? So if this is 2.5 volt, what is the VGS here? 2.5 volt. What is the VDS here? 3 volt. Okay. Now VGS minus VT. Let's say for this particular MOSFET, VT is 0.5. So VGS minus VT is 2 volt. Okay, that is VOV. I just told you that with this VGS minus VT is overdrive voltage. Okay, and this is less than VDS. So for saturation, VDS should be greater than equal to VGS minus VT. Now 3 is greater than 2. So obviously this MOSFET will be in saturation region. Okay, so this is one of the biasing circuit. Okay, now I will give another example of biasing circuit. Okay. Just give me one thing. Now this is also a biasing circuit. I just briefly say about the biasing circuit, because if you don't know what is the biasing, then these small signal things will be like not that much clear. You will not feel. Okay, the intuition is more needed than the particular concept. Let's say this is RD. Okay, and this is say RG. Okay, now see what will happen here. What will happen here? Let's say we set the voltage here. The MOSFET is in saturation. Okay. The thing is okay. Let's say this is let's say this voltage is 3 volt. I gave you this voltage 3 volt. Then what will be the current here? Can you say what is the current here? This is 5 volt and this is 2 kilo. Can you say what is the current through the MOSFET? The current through the MOSFET, what will be the current here? The current should be flown here because no current will flow through here. So 5 minus 3 by 2 will be our current from the MOSFET. So from MOSFET, the 1 milliampere current will flow. This is clear or not? First tell me.
Yes, sir.
Okay, now if this is 3 volt, and no current is passing through here, what will be the drop here for this RG? Is there any drop in RG? Hello? Hello, am I audible? Hello? Am I audible, guys?
Yes, sir.
Okay. So my question is there any drop in RG or not?
No, sir.
No drop. So if there is no drop here in RG, what is the voltage here in gate?
3 volt.
3 volt. So if the gate voltage is 3 volt, the drain voltage is 3 volt, then let's say this is also 0.5 volt VT is given. Okay. Now VG, what is VGS? 0.3. What is VT? 0. Sorry, it's not 0.3. This is 3. This is 3 volt. Okay. And what is VDS? 3 volt. This VGS minus VT will be 2.5, and that is obviously less than this 3 volt. So this MOS will be in saturation region. Right? Right? Everyone got?
Yes, sir.
Yes, sir.
Okay. Hey guys, are you like feeling heavy or not? Like, are you like not getting the concepts? I am just noticing that you guys are not replying. If you guys are not getting, there is no point of discussing also. Okay, I will discuss some like I will move my level to the like I will decrease some level and then I will move from the base also. Are you getting or not? I'm giving these concepts out of this like activity question discussion because I think for an undergrad level course, this if you guys know this kind of concepts, ultimately you have to get some job, right? So for this kind of questions are asked in the interview also, and MOSFET is one of the like favorite topics of interviewer. That's why I am stressing a lot about MOSFETs. Okay, because that thing are using that MOSFETs are used in the industry. Okay. BJT is also used, but BJT is not that much. The application of MOSFET is like way much higher. Whatever phone, laptop you are using now, these all are like processors, chips are made by the MOSFET itself. Even if the op-amp is also made by the MOSFET. Okay. So, so these are the two bias stabilization circuit. So I discussed this. This is one of the bias stabilization circuit. This is one of the bias stabilization circuit. There are another bias stabilization circuit also. Okay. Even the current mirror is one of the bias stabilization circuit. Okay. Now, what I will do, I will discuss the small signal thing. Okay. These whatever I discussed till now, that is whole about the DC things. First, I talk talk about it in the last class. First, I told you for amplifying a circuit, we need a MOSFET. For use the MOSFET as amplifier, we have to bias the thing. Then we can use it as a amplifier. Now the thing is we are biased. Now I am assuming this MOSFET have an internal circuit which has biased this. Okay. Now you have to give the small signal voltage. Then I am saying that how I will give. Let's say this is the biasing circuit. Let's say this is the biasing circuit. Okay, and this is the total arrangement here. We are going to take some voltage here. This is our load resistance RL. Okay, this is our voltage V out. Now this is the voltage V out, means this is the small signal voltage, amplified version of voltage. This is small. Okay. Small V out. This is the amplified signal. Now till now we didn't give any input voltage, right? This is, let's say this is R1, this is R2. So no input voltage is given. So you have to give some input voltage to the gate. Okay. It need not be to the gate only. You can give at any terminal whatever we are needed. So according to the input, at what terminal you are giving input and at what terminal you are taking output, according to that configuration, the amplifiers are like characterized. That's why you have three amplifiers: common gate amplifier, common source amplifier, common drain amplifiers. You remember now this kind of amplifiers? Okay, that's why this kind of amplifiers came. According to at what point you are giving an input and from what point you are taking output, those will define what type of amplifier it is. Okay. Let's say for this case, for this example, we are taking our input here. So this is plus minus Vi we are giving, and we are taking output from here. Now see, the thing is, if we directly give an input signal here, okay, let's say this is an input sinusoidal we are giving. Okay, now if we directly give this input signal here in this gate voltage, now this gate voltage will also vary, right? This gate voltage also vary. Now if this gate voltage varies, this current will also vary now. Okay, that will disturb this drain current. If this is capital, what does it mean? This is the DC current, right? Now if this small signal is directly given to the gate voltage, this DC drain current will also be disturbed. So we cannot disturb the bias stabilization circuit. So the bias stabilization circuit has to be fixed. This bias stabilization circuit has to do the work, okay, in the DC condition. So we cannot directly apply this small signal thing. So for that we have a particular mechanism. Okay, that particular mechanism is this a capacitor we used. This capacitor is called as coupling capacitors. Okay, these coupling capacitors are used to couple the input voltage and to take the output voltage. So the thing is, we can't directly take the output also. Okay, these coupling capacitors are given. Now the thing is, do you know why this, like, it's okay? The thing is, it's okay that we understood that if we directly give an input, that will disturb the DC bias stabilization circuit. So we can't give the input directly. That's why we are using a coupling capacitors. What else? What else is the reason? The thing is, if we directly, let's say if we directly connect the output here. Now this is DC. Some current is flowing here. Some DC current is flowing here. That is ID. So some DC drop will be there, right? Some DC drop through RL will be there.
Yes, sir.
So if some DC drop will be from there, the output will be also DC. Okay. So that is not amplified itself.
That's
Okay.
why capacitor is used.
Yeah.
To remove the DC part.
Yeah. So to remove the DC part also, we are using that. And generally, these small signal things are small incremental signals. Okay, that are changing. That's an incremental changer. The signals are incremental. The incremental means that is constantly changing or changing from particular point. Let's say this changing signal is sinusoidal. So this coupling capacitor will allow this sinusoidal signal, and also this coupling capacitor will also remove the DC part also.
Yes, sir.
So that's why these coupling capacitors are used. So this is the whole picture of a particular MOS to work in a particular circuit. This circuit is also amplifying. This circuit is also biasing the particular MOSFET. Okay, this is the whole picture. Now till now, all the concepts I discussed you got or not?
Yes, sir.
Okay.
Yes.
Now we have discussed DC things. We have discussed the biasing circuit, and we have also discussed how to give the input, the small incremental signals or the small signals to the MOSFET also. Now these things, three things we have discussed. Now we have discussed only how to give the signal. Okay. Now how this MOSFET is amplifying this incremental signal, we don't know. Okay. So to know this particular thing, we have to model, like we have to, like what we know now, we know some KCL, KVL, some Ohm's law. Okay, this thing we know, right? Now we have to analyze a particular circuit using these only. Okay, now in this circuit, this MOSFET is a device. Okay, we can directly apply this KVL, KCL and Ohm's law. Now to applying this particular concept and to analyze the circuit, we have to model a particular MOSFET in such a way that this particular KVL, KCL and Ohm's law we can apply to the circuit and analyze that, right? Hello?
Yes, sir.
Yeah. So we have to model the MOSFET, right? And model the MOSFET for what region? For small signal. Okay. Now we are going to do some small signal analysis. Till now we haven't done any small signal analysis. So for doing the small signal analysis, this much base is needed. Okay. Now, what is this small signal analysis? This small signal analysis is modeling a particular device only. After that, it is fine to like use the KVL case, that everyone can do, right? So the MOSFET, let's say the NMOS, the incremental picture of this is look like this. Now someone can question that why it look like this. That is out of your scope actually. If I go to derive that, okay, first of all, very few people will understand that, and second of all, that will have no use actually. Okay. Okay. So this is VG. This is small signal. Okay. This all are small signal. Okay. This is source, this is gate, this is drain. Okay, so this particular thing is VGS, small signal. Okay, now this is voltage is VGS, this current is GM into VGS. Now I will discuss what is GM, don't worry. Okay, till now I didn't discuss what is GM. GM VGS. Okay, so and what are the terminals? This is the gate. This whole thing is a source. Whole thing is source. This is one node, and this is the drain. Okay. Now we can model this. And the thing is, we can also include one more term here. This is R0. Okay, that I discussed. The drain to source resistance. Remember, this is our VDS, this is our ID, right? Now the current varies like this, right? It should vary. The ideal MOSFET will vary like this, but the practical MOSFET will vary like this only, right? Huh? Now this slope is very low. That means the resistance is very high or very low. If the slope is very low, that means by the change in voltage, by the much change in voltage, the current is changing very little. That means the resistance is very high or very low. Hello?
It is high.
It is high because we are, let's say we are changing 100 volt, we are changing 100 volt, but we are getting a very little current. Okay, so
Yes, sir.
voltage divided by current, voltage is very high, current is very small, the overall quantity is very high. These particular slope is R naught, and this R naught formula you can remember, this R naught is 1 by lambda into ID. Okay, this lambda will be given. Okay, now you don't need to remember all of this. Okay, you will not, by practice you will came. Okay, and this thing are like, this thing is little bit advanced level. Okay, but thing is you should need to know. And the thing is, this is not that much fascinating also. Like the simple model itself, a simple particular voltage source that is controlling a current source. This particular voltage source is controlling a current source, that is the voltage control current source, and those current source have an internal resistance of this. Okay, a practical current source, that is the internal resistance of this. We know a practical voltage source has zero resistance. A practical ideal voltage source has zero internal resistance, and a particular current source has infinite internal resistance. Okay, for practical thing, the source, the resistance is not infinite. Okay, see, in a circuit nothing is zero, nothing is infinite. Okay, you remember this. Okay, in practical scenario, if you want something to be zero, you will not get a zero. Okay, you want your problem, you want that that you, it's, I'm giving a simple example. Let's say you want a full VDD voltage, that means you want the full marks in your exams. Okay, but there is a full marks. Okay, and like for the same thing also, like you want that your life problem of your life will be very, should be zero, but the thing is you will end up of having a lot of problems in your life. Okay, so this is the same thing. In the practical scenario, if you want something to be zero, you will not get that, and if you want something to be full, that will not be full. Okay, so this is the particular thing. And this ID is a, what is this ID? This ID is a bias current. Whatever current is passing through the MOSFET, that is your what? That is your ID, right? Till now, is there any doubt? Hello.
No, sir.
Okay. Now we'll go to some circuits. Okay, and we'll quickly solve. Okay, some circuits. Okay. And one more thing, I talk about this lambda. Okay, do you know what is this lambda is? What is this called? This is called as process technology. This lambda is defined by a process, like process technology. Like let's say you want to make some device. Okay, let's say a company called TSMC is making some device. It's making some MOSFET. Okay, and after making the MOSFET, it found out that this lambda parameter is fixed. That is called that, this is some 0.2. Okay, so this particular thing is fixed by the particular technology itself. Okay, in different type of technology, like different type of technology means this 180 nanometer technology, this 120 nanometer technology. Okay, this particular in the, with this technology parameter, this lambda is also valid, and this is constant part of for a particular technology, right? See, so this is our whole background to start. And for the PMOS also the same thing. PMOS also we can model the particular MOSFET. Achha, first of all, tell me what is the source here. This is A, this is B, this is C. What is the source here?
A is source.
A is source, B is gate, this
Gates
is
to drain.
drain. Okay. Now we can model this as same like this, same. This R naught, just the terminal is changed. Plus minus VSG, this small signal. This is GM VSG, and this is R naught. So this is source, this terminal is drain. This whole terminal is drain. This is gate terminal, this is source terminal. Got a small got the concepts? Okay. Is there any doubt till now?
No, sir.
Okay. Now you guys have read about common gate, common source, and common drain, right? Right?
Yes, sir.
Now I will quickly go through with those amplifiers, okay, and we'll discuss those amplifiers. So by what factor we have characterized these particular amplifiers? What is the characterization factor of these amplifiers? I just now told some times ago. This is the thing, like to characterize these things. Okay, we have two parameters, input and output. Okay, so at what point we are giving the output and at what point we are taking the output. Okay, that will define what amplifier it is. Okay, now see, I am drawing something, and this is a small signal picture I am already saying. Okay, so for that small signal picture, this capacitor, this coupling capacitor will be there, that will be short circuited, right? In the small signal, this AC part, this capacitor act as a
Short
short
circuit.
circuit,
Yeah.
and inductor act as open circuit, right?
Yes, sir.
For the small signal, capacitor acts as short circuit and inductor acts as open circuit. And for if there is a voltage source, independent voltage source, not okay, not the simple voltage source. Independent voltage source is there, that will be act as short circuit or open circuit. Can someone say? If there is an independent voltage source is there, what thing it will act as? According to what thing? That will, all the independent and the small signal picture, all the independent sources will be replaced by their internal impedances. Okay, if there is a independent voltage source is given, what is the internal impedance of an independent voltage source? Hello, am I audible?
Yes, sir.
Hello, only one girl is replying me. Everyone is like sleeping. Are you there?
Yes, sir.
See, these kind of things will be important. That's why I'm giving this thing. Like, our instructor also didn't told me to give this kind of contents also. They only like, my duty is only to discuss the activity questions. I'm giving this kind of concept because this kind of concepts will be needed. Okay, this kind of concepts, like if you ignore this kind of concept while going to the industry also, you will face some difficulty. Okay, so see, now we don't know what is this. Okay, so independent voltage source will having a internal impedances of 0. That's why if the impedance is 0, that will act as short circuit. If an independent current source is there, that will be replaced by a open circuit. Okay, these four things you should know. Capacitor in small signal will act as short circuit. Internal independent voltage source in a small signal will act as short circuit. Inductor, open circuit. Current source, open circuit. Okay. Now let's say this is RD. So previously this was VDD. In the DC DC voltage source. So this will be grounded or zero. Okay. This was already grounded. So this is zero. Okay. Now we are giving an input voltage here, Vi. Okay. Now I need to know what is the output voltage. Okay. Now let's draw the small signal picture. Then these all the small signal, right? This V0, Vi, these are all are small signal, right? So this is our picture then. So this is, and let's say R0 is infinite here. This, I am making your life smoother. Okay, this R0 is not there. This R0 is infinite. Okay. So our MOS circuit will look like this only. This will be GM VGS. What is VGS here? What is VGS here? What is VGS here? Can you say me what is VGS? VGS is VG minus VS. What is VG?
Voltage at gate.
Yeah. What is given? I know it is voltage is given. Voltage is gate. What is given? What is the value of VG is given? That is VI. See, this is VI is given, no?
Oh, yeah,
I told you this is VI. And what is the source voltage here?
It is grounded. It is zero.
Zero. So what is VGS?
Vi.
VI. So this is GMVI.
Okay.
Okay. Now what else? I told that this R0 is infinite. That means it will be open circuited in the small signal picture. See, this R0 is open circuited, infinite. Okay. Now this is infinite, and the thing is, see here. So here is our drain. Here is our drain. So from drain to ground, there is one resistance. Now this is the source. This whole terminal is the source, right? Whole terminal is source.
Yes, sir.
Now this source is also grounded. This is grounded. Okay. And from this drain to ground, there is a resistance, that is RD. So if I draw the good manner, okay, it will kind of look like this. Okay. RD. So this is okay. So this is the incremental picture, and this is our V0, because we took the drain voltage as our output voltage, right? Now see, what is the current flowing here? What is the current flowing here?
ID.
Not ID. See, what is this? A current source, right? Dependent current source.
Yes, sir.
So, and what is the value of that current source?
GMVI.
Exactly. Now someone answered me that ID. See, ID is what? ID comes in what picture?
In DC.
In DC. Now we are discussing what?
AC signal.
Yes. So ID will come or not?
No, sir.
So all the DC parts now
Yeah,
will not come here.
It
So
will
any DC.
small ID.
Yeah. So whatever you are seeing here now, it is all a small signal.
Yes, sir.
The thing is, so what current flowing here is GM Vi. So current will flow here also GM Vi. Okay.
Yes, sir.
So the voltage drop will be here equal to plus minus plus minus like this only. So and voltage drop will be GM Vi into RD. So V naught equal to minus GM Vi RD. So V naught by Vi equal to minus GM RD. Right?
Yes, sir. Now I get it.
So that's why. And do you know what is the name of this circuit? This is a
Common gate.
source
Okay.
common source amplifier.
Okay.
Because see, source is common. Source is grounded.
So
Right? Source is grounded. And we are giving a signal in gate. We are taking the output from the drain. That's why this is a common source amplifier. Source is common to both gate and the drain. Now, what is the gain here? Gain means what input we are giving by what output we are taking. Like, so V naught by Vi is our gain. Okay, and this is minus GMRT. So in common source amplifier, we get the gain negative gain we are getting. Let's say we are this GM is 8 millisiemens. Okay, and this RD is 50K. What will be your gain? This is 8 into 50. That is what? 400. So this V naught by V will be 400 and sign will be minus. So we are giving an input voltage of, let's say, 1 millivolt, and we'll get 400 millivolt as output minus 400 millivolt as output. So we are getting the gain, right? So we are amplifying the signal, right? This thing clear or not?
yes, sir.
Okay. Now the thing is, I talk a lot about these amplifier things, these things and those things, and I ignored one thing. What thing I ignored? Is I haven't discussed GM. I just wanted to show you what GM does. Now you see, I told you in the beginning. I told you this GM is a tool of amplifying a particular signal, right? Now I proved you with the example that this GM is indeed amplifying a particular thing. Okay. Now just first I have to give the feel what GM does. Then after I will discuss GM. Okay. Now see what GM does. How GM comes. GM is trans. What is the name of this?
Transconductance.
Yes, transconductance. Okay. So how this GM came. See, GM is the effect of input to the output. Okay, GM is the effect of input to the output. That means, like, see, a particular mic. If I talk in front of a particular mic, okay, so my voice is the input to the mic, right? My voice is the input.
Yes, sir.
Okay, and whatever with the sound which are like reflected to everywhere, that is the output. Okay, so I am giving some input to the mic, and that mic is amplifying my voice. Okay, and that increased my sound, and we all can hear, right? So that is the work of a mic. So we can assume that mic as a amplifier. Okay, and the input is my voice, and the output, the sound you are getting. Okay, so GM is the effect of my input, my voice, to the output. What is GM doing? GM is taking some signals, okay, and it's doing something, and it's giving some output. So I can say that whatever be my change of output, so GM equal to change of output due to the change of input, right? So we can say that GM is the measure of change of output by change of input, right? We can say that. Let's say we are giving a 1 signal and we are getting a 50 signal. From 0 to 1 signal we are we are getting 0 to 50 signal. Some measurement 0 to 50, whatever, I don't know, something. Okay, so we are giving this much change, we are getting that much change. So that is the basic purpose of amplifier, right? Hello, are you
Yes,
getting or
sir.
not?
Yes,
Yes,
sir.
sir.
Okay, so what I say, so GM is the effect on output due to the change of input. So this is the effect on output. Effect means what? The changing of output, right? Whatever be the output is changing. Okay, and what is the effect of input? Like whatever be my input is changing, right? Let's say in another example, let's say we are driving a bike. Okay, and we are like we are rotate the accelerator a little bit. Okay, now that accelerator have an initial point, right? Let's say this is our accelerator. Okay, and this rotating like this only. Okay, if I rotate like this, the speed will increase from this side to this side. So let's say this is the initial point. Okay, let's say the accelerator is increased to this point. Okay, so while the accelerating in this, the speed was let's say 20 kilometer per hour. Okay, and while this much is rotation is there. Okay, let's say my speed is 100 kilometer per hour. Okay, now I have changed my input to this only, and we get the change in output to this. So our change in output is 80 kmph, and let's say we move this something one bit we move. So this is our change in input, this is our change in output. So our GM will be this 8 by 1, matching the like whatever be the units that should be considered. Okay, so you got now this, sorry, this is 80. You are getting what is GM is doing. Hello.
Yes,
Yes,
sir.
sir.
Okay, so this is the physical interpretation of a GM. Okay, now in a particular MOS circuit, what is the output? What do you want? ID, right? This ID we want, right? So output will be in terms of ID. So ID is what is the change of output. So change in ID. Okay, by the change, what is the input here? What is the input here? What is input? What input we have gave here?
VI.
VI. So VI means gate voltage. Change in VG. Sorry, VGS. Right?
Yes, sir.
So we can see that this is DID by D VGS. Right?
Yes, sir.
So we know what is ID. So DVGS of VGS of, what is ID here? In saturation, mu n 1 by 2 mu n Cox W by L VGS minus VT, right? Whole square.
Yes, sir.
Now this whole mu n Cox W by L is constant, so it will came outside 1 by 2 mu n Cox W by L. Now if we derivate it, it is like VGS square, right? Simple derivative 2 into VGS minus VT, right?
Yes, sir.
So these two cancel out. So our GM will be mu n Cox W by L VGS minus VT, right? Okay, this is much clear.
Yes, sir.
So if I, let's say, if we write like this, 1 by 2 we multiplied, sorry, not, so this is our one expression. First remember this. So this expression tells us GM directly proportional to VGS minus VT, right? Because these whole things are constant. Is much clear or not?
Yes, sir.
So if we multiply this is multiply, sorry, this is multiply in this expression. We multiply 2 and 1 by 2, okay, and then we are writing like this: mu n Cox W by L VGS minus VT whole square into 1 by VGS minus VT. We can like write like this, right? The same expression I have written like this only. Can I write or not? We just multiply and divided 2 and 1 by 2 and VGS minus VT and 1 by VGS minus VT.
Yes, sir.
So this is a known expression. What is this? What is this?
ID.
So 2ID by VGS minus VT. So GM is also like this. You can write the GM also like this.
Okay, sir.
So another thing, we can write another thing. So see. This expression is saying the first expression is saying that GM is proportional to VGS minus VT. But this expression is saying GM is inversely proportional to VGS minus VT. Now someone can say that what you are writing, sir. So at some time you are saying that VGS minus VT is proportional to GM. At some times it is inversely proportional. Now your two statements are contradicting each other. How can it be possible? Same quantity is directly proportional to some quantity, and the same quantity is inversely proportional also. Is it possible? No, na? Then what is the right expression? So some of like some logic is like we are missing. So what is the right expression? Is both expressions is right? If someone says that, sir, one expression is wrong, that can't be possible because I have simply manipulated the example, manipulated the same expression. The thing is, see, this ID have this VGS minus VT whole square, and that will be cancelled out by this factor. So ultimately, it says VM is directly proportional to VGS minus VT itself. This is the another way of writing it. Okay. So there might be some question to confuse you also. In some question, this particular expression is helpful. In some particular this particular expression is helpful. Let's say in a particular MOSFET, you don't know what is that drain current is flowing. At that time, this first expression will be helpful for you. But at some particular example, let's say mu and C of W by L is not given, but you know what is the drain current. So at particular that example, this GM expression will help you. Okay?
Means both expression are right.
Both expressions are right. Yes.
Okay.
Yeah. And one more expression is there. Can someone say that? Can someone manipulate it a little bit more? Okay, I am doing for you. Okay. See, we started our expression. Let's do it. So let's say mu n Cox W by L VGS minus VT. Right? Okay. Now, can I write like this? It is root over of mu n Cox W by L VGS minus VT. This whole thing square. Can I write like this or not?
Sir, why root under?
Because this is a square, right? The square and root is cancelled each out, then I will get the first expression.
Okay.
Okay. So now see, if I write it like this is mu n Cox W by L into mu n Cox W by L VGS minus VT whole square. Can I write like this? Can I write like this or not? I just like this was a square term. I just take one square term outside. Right, like this
Yes.
or not?
Yes, sir.
Okay. Now see, if I write like this only, let's say 2 into mu n Cox W by L into 1 by 2 mu n Cox W by L VGS minus VT whole square. Can I write like this? I just multiply 2 and divided by 2. Right? Now see, this expression is on again known to us,
ID.
ID. So this is 2ID
Oh,
mu
it
n.
will be 2KID because this was the constant nu and
Yeah,
C1.
I mean, yeah. Oh, sorry. Why I did like this? Okay. This will be L. Now see, at what time it will be useful to us? Let's say our gate overdrive voltage we don't know, but we know mu n Cox W by L and ID. Then this expression will help us. Okay.
Yes, sir.
So we got the idea about GM or not?
Total, we have 3 expression of GM, right?
Total we have 3 expression. All the 3 expression I have written.
Yeah.
First depends does not depends upon ID. Second does not depends upon mu n Cox W by L.
Yes, sir.
And third does not depends upon gate overdrive voltage.
Yes, sir. Got it.
Okay. So so the thing is 3 parameters are there: ID, mu n Cox W by L, and VGS minus VT. Minus VT. If any of one, so these 3 parameters, like any of the 2 should be given. Okay. If all the 3 is given, you have the full access. Okay. If any one of the parameter is not given, you have the solution. You can use only 2 and you can get the GM value. So what is the hierarchy? So first, to analyze the small signal, you need to know the GM. To know the GM, you need to analyze the circuits in DC. DC analysis is needed because see, this ID mu and ID and VGS minus VT are the DC quantities, right? So using those DC quantities, you will get GM. Okay. So first, so what is the procedure of analysis? What should be the path of analysis? So first, you need to do the DC analysis. After doing the DC analysis, you got this ID mu and Cox, sorry, ID VGS minus VT. Okay, these kind of things you will get. After that, you will calculate GM. After that, you will go for small signal analysis. Okay, you got?
Yes, sir.
So this will be our path. So that's why I spent a lot of time on DC operating points. Okay, so without doing the DC, you can't analyze the circuits in AC. Okay, so I will briefly discuss all the amplifier circuits. Okay, and we will end the session. Okay. So till now, do you have any kind of doubts? First, tell me. Then I will summarize.
No, sir.
Everything is clear, right? And you guys are like getting the concepts or not? You guys
Yes.
are getting, right? Okay. So these things are like, if you go and solve some questions now, you will feel that how needed is this thing. The thing is, everyone will say this is the GM formula, this is the ID formula. Okay, but how it comes, that process should be needed. That process should be in your mind. Okay. Now see. So we have 3 amplifiers. We have main 3 amplifiers. What are those? Please tell me the names. Please tell me the names. This is common.
Common gate amplifier.
First, we will discuss common source. Okay, because
Okay.
that is discussed in the class also. Okay, professors also
Then
discuss
common
common source.
gate.
Yeah, common gate and common.
Then common gate, then common drain.
Yes. Common source, common gate, and common drain. Okay. These three amplifiers are discussed. Okay. Now, that's I will discuss only the small signal configuration. You all guys know how to from small signal you can from the small signal configuration you can also go to the DC configuration. You know the all biasing circuits. So I will discuss only the small signal. Okay. And please guys try like from this DC, from this AC small signal circuits, try to make the full circuit one full circuit configuration I have given to you. Okay, that is a small signal full circuit of the common source amplifier. Please try to make both common gate and common drain. If you do that exercise now, that will make your concept so easy. And I have also gave you two biasing circuits, not one. Okay, also try to find out by yourself, is there any other biasing circuits are there. Okay, MOSFET is the most important topic. MOSFET and op amps are the most used analog devices. Okay, like these MOSFETs and all op amps are very useful. Okay, everywhere it is it is used. Okay, this is V naught. This is our VI. Okay, R D. Okay, let's say this is GM is given. Okay, GM is the parameter of this particular transconduction of this amplifier. Okay, so the voltage gain AV. AV means V naught by VI equal to minus GM RD. I discussed till now. So we can say that. So if some 1 volt is given and the if gain AV equal to let's say 10, then we'll get the output as minus 10, right? 10 volt. So if this is VI and this is V naught, so 180-degree phase shift was there, right? We are like, let's say we are giving input voltage at this particular axis, and we are getting the output voltage at there. We're giving some in positive voltage, you are end up of getting a negative voltage. Okay, that's why your 180-degree phase shift is there. That's why we can say that from input to output, 180-degree phase shift between output and input. So let's say if in a particular circuit, if you want to take what if you want to give some input, and if you want 180-degree phase shift should be there, okay, then your preferable choice should be a common source amplifier. Okay, now for a common gate amplifier, this is the configuration. The gate should be common, right?
Yes, sir.
So I'm generally in a particular circuit, the common gate amplifier is used for a current source. Okay, it's a current buffer, but current buffer is also like that circuit is with the current source is also discussed in the class also, but it's not, it doesn't mean that you can't use as a voltage source. Okay, so like if you want a current buffer, then this circuit is a preferable choice. Okay, this is also called as current buffer. Okay, so this is RD, this is V naught, and this is V in. Let's say this is, so input we gave at the source. Okay, and we take the output from the drain. Here the voltage gain A will be GM RD. You can analyze the same way that I analyzed the common source amplifier. So in this circuit, the voltage gain here and here is same. For the common source and the common gate, the current gain is same, the voltage gain is same. But here in the common source, it is negative, here it is positive. Let's say, so for this circuit, you can use at that situation that where you don't need to invert the sign. Okay. Am I audible now?
Yes, sir.
Okay. So here phase shift, how How much phase shift is there? 0 degree phase shift, right? We are giving a positive voltage, we are end up getting a positive voltage itself. And this is called as current buffer itself, because current gain, this is the voltage gain, right? Current gain here will be 0, sorry, 1, because whatever current will be here pass through here, it will the source will have the same current, right? So whatever be the source current will be the same as the output current. That's why the current gain is 1 here. And last, the common drain. Okay, common drain is called as source follower. Why? I will tell. Okay, don't worry. Source follower. So the configuration will be common drain. So the drain should be common. Okay. So we're giving an input here. Okay. Vi and getting an output here V0. Okay. So our gain will be here. The gain will be, you can analyze it. Okay. Our gain will be GM. Let's say this is RD. So sorry, this is let's say this is RS, because the source is our terminal, right? This is RS. So gain will be GM RS by 1 plus GM RS. You can analyze whatever be the small circuit I given you. You can analyze it, and if you don't get the answer, I will take another class. Maybe in this week itself, I will take another class. On that class itself, you can say me. Okay. Maybe tomorrow or day after tomorrow, I will take another class to discuss the activity questions of week 11 and week 12. Okay. So we can discuss that. Okay. If you don't get any of these answers, so our voltage gain will be this one. Okay. And take R0 will be 0. Okay. R0 is 0. R0 is infinite. Take R0 is infinite. No drain to source. This R0. You don't need to take this R0. Okay. I just told you for sake of completeness. But for your levels, the R0 will be always infinite. The question will be set as that. And even if R0 is not infinite, you know how to calculate this R0. I also told you. Okay. And to include the particular particular circuit to calculate all the voltage gain, current gains, this R0 is simply, you need to apply simply the current KVL KCLs, not much more than that. Okay. I gave you the full model. If you can't do that, and if you want me to do some analysis with the R0, you can tell me in the next class. Okay, I will discuss for you. And this also, so this voltage gain having no sign change, right? So if you give some voltage Vi, you will have some voltage also. Now, can you, with this configuration, can you say that how much the maximum voltage gain here? How much maximum voltage gain we can get here? GMRS by 1 plus GMRS. Hello?
Oh, it will be 1.
Maximum is 1. So that's why we can't get the voltage gain here. Okay. We can't get the more voltage gain here. Okay. But this circuit have a particular advantages. Okay. This circuit have particular advantages. Okay. So you try to find out what are the advantages. Okay. Everything I will not say. You have to work some by your own. Okay. So here also 0 degree phase shift is there, because whatever be the voltage we are giving, if we give some positive voltage, we are end up of getting positive voltage itself. So V0 by Vi will be maximum is 1, and that is positive also. And this is called as source follower. Okay. So see, if we give some voltage here, so let's say this is 5 volt, and this GMR is very high. So if this GMR is very high, this will be 1, right? Approximately 1. So if we give some 5 volt, we will end up getting a 5 volt. Okay, that's why it's called as source follower. The source is following the gate. Okay, that's why it's called as source follower. Okay.
What is the output impedance, high or low?
Okay. Now this thing you have to like I will not next class. Okay. First you like try to find out what is the output impedance here. Here, what is the input impedance here? First tell me. What is the input impedance here?
Low.
Low. How to calculate input impedance? What is the input here? Our gate terminal is input, right?
Yes, sir.
So if we apply some voltage here, plus minus some test voltage if I apply, so you need to measure some current, right? So if we apply some voltage here, is there any current flow in the gate? No current flow is there, right?
Yes, sir.
Because gate will not allow to flow some current.
It works like
Okay, if
insulator.
no current is, yeah, it works like insulator. So if no current is flowing, then R in is infinite. So at whatever configuration you used, okay, whichever configuration you use gate as a input source, input terminal, then that configuration will having an input voltage of infinite. Okay, infinite, like there should be some terminal, there should not be some parallel resistances. If some parallel resistance are there, then that parallel resistance will be our input resistance. But if there is no parallel resistances, okay, then our input terminal having the infinite resistance, R in will be infinite. Now your task is to calculate what is the R out for the circuit. Okay, so in the next class we will discuss the R out for the circuit. Okay,
Okay, sir.
to how to calculate the R out. So at the output terminal, you should apply some test voltages and measure the test current. So output terminal is here. Okay. So you should disconnect all the source voltages and current by their internal resistances. Okay. And you should consider the small signal circuit, and you should calculate what is the current that is flown from that circuit, from that test voltage. Okay, so that test voltage by test current will be your output impedance. Okay.
Okay, sir.
Okay, end of the class today.
Okay, this will be the end of the class today. Okay, so anyone have any doubt? Anyone have any doubt today?
No, sir.
Okay. Okay.
Okay,
Okay,
bye.
you can leave.